who are on. Bill, you asked about a heat box. You are working on 133, 134, and 134 is the activity with the heat box, and 133 really just great thermo practice problems. In fact, if you look on my website, you'll notice that my review for thermo is not very big because I think 133 is such a great review of all the information. But 134, if you're going to do that, you either have to build a heat box or buy a heat box. And Adam, you have built ones because you did yours from when we prototyped them, right?
Correct. Yeah. Yeah, they're not that difficult to make. Really, you just need a light bulb and a plug and a board and a couple pieces of foam. So.
Right. And did you put plexiglass on yours at all?
Yeah, I
that's
did.
The expensive.
Yeah, you can get
plexiglass is the expensive part. You just don't have to get very thick plexi, because it's really just supporting. And on 4 sides, it's got the foam anyway, and you can put a board on the bottom to mount the light bulb. So, and then you want plexi for the top.
Okay.
But it doesn't have to be very thick.
Okay, like 1/4 inch. Do you think that would work?
Yeah, I think so.
Yeah, I made mine. Okay. I'm trying to remember. I think I made mine a 1/4, but I think the actual box is the one that you buy. Is that 1/8? I mean, I think 1/8 would even be fine. It's just a matter of trying to contain the heat that's coming out of that bulb. The energy is coming out of that bulb. You're just trying to contain it a little bit, make it somewhat airtight.
Okay. Yeah, I think the store-bought ones are a 1/4. The only piece that I'd really concern myself with would be the top. Because you're going to have support on all the other sides. So if you're making more than one, as many sets of temperature probes as you have and money and time to make boxes, just because you can run more at once that way, if you're going to buy, maybe buy 1/8 for the sides and 1/4 for the top.
Okay, I've got time to make them, so, because I don't know if we'll get to 134 this week or not, hopefully.
Okay. And you can always run, you could always run 1 or 2 if you wanted to. I mean, have kids bring it in and then have you guys, the class, vote on, like, which 2 they wanted to compare. And you could just run 2 of them this year, you know, and do over a couple of days or something if you're, you know, having to try and squeeze in making them. I think it's a good activity. I think it's a little hard for the kids to follow the kind of the instructions. So I wouldn't like just turn them loose and walk away because there's going to be some questions. And then I also don't know if I think the instructions at the beginning are really clear, but one of the probes goes, do you have like the temperature probes?
Yeah, I do.
Okay, so whatever your insulation is, you're going to have to stick that temperature probe through the insulation into the box. So you're going to need, or if since you're designing your box, like if I was building mine, I would make a hole on the side really high so that you could just go through the side, not to go through the insulation.
Okay.
I have log tags, so I don't have to go through it. Mine just mount inside. But then, you know, run those. But one goes on top of the insulation and one goes inside the box. And the instructions kind of say, just like, place it in the room. So, but one goes on top of the insulation, one goes inside the box.
Okay.
Tricia, are you online? Maybe on phone, it looks like.
I see her name. She's listening.
Okay. So you have a question, Tricia? You're having trouble with sound. The question is, so you might not be able to hear it. So I'm going to let you answer that for a second. Let me talk to Cassandra. I saw that you were on. Fuel cell cards. I do this lab. I think Adam skips this lab. What is the outside temperature like right now where you are?
25
25. So you're going to either have to go do this inside with like what I call chicken coop lights, like the big floodlights. I have to be honest. I do it when I can go outside and all my kids can run their cars at the same time, and we just use the sun as the solar power. It's cold. I would maybe this year skip it. Adam, what are your thoughts on it?
If you're running just off the solar panel, the solar cell or whatever, yeah, you can have them chase with a light if you really want them to. If you're charging the fuel cells, I just charge them with the power supplies.
Yeah, maybe charging with a light bulb, charge the fuel cell with a light bulb, though that takes an inefficient amount of time too. If you have
Did we lose everybody?
I'm here, but I just called in. This is Trisha.
I'm still
I can
here.
still see y'all too.
Okay. It's freezing up for some, and I can't hear Karen right now. I can sort of see her moving.
I could see Karen and you moving, but I could not hear you using the headphones, so I just called in.
Interesting.
I just lost Karen.
I think she just logged
Karen
up
did this
and
week.
logging back on.
Okay.
Now, what are you going to do? First meeting of the new year, right?
Well, if it's any consolation, all of my computers in the IED where we're using the Autodesk Inventor, those all, wireless connections, and kids can't log on, and I don't know what happened over the new year. Licenses expired. It's like, what happened?
That's always fun, especially when a lot of people are off. Over that New Year's switch, a lot of people are off, so they don't, if problems happen, they don't get them fixed right away.
Well, all I can say is if a chunk of the students weren't missing, I don't know what I'd be doing, because I'm like swapping this kid's computer for that kid's computer, and that's the only way to make it work.
Yeah.
Ugh.
That's the part that they don't teach you in college.
They didn't teach me any of this.
Yeah. How do you switch and get everything to work? We see you, Karen. Let's see. Is anybody that's not on a phone able to hear me still?
I can hear you, but I'm not on a phone.
I can hear you.
I can hear you.
Okay.
Karen's still frozen though.
Hey, now we see two of her.
Oh, yeah, that's fun.
Different times.
Hi. My Go meeting said that Go meeting was not functioning anymore. Sorry.
Yeah, it was kind of happening to a bunch of people.
Okay. It's not personal then. Awesome. Did everybody work through the fuel cell cars while I was gone?
Yeah.
Sorry about that. Stress strain simulation. Trish, did I hear you there? You had a couple questions about reverse engineering and simulation for stress strain. I don't do the reverse engineering project. My kids do that in both middle school and the IED class, so I don't do that. But the stress strain on 232, instead of doing the SSA, which is a stress strain analyzer, use the simulation. It's just another choice on 232.
Okay.
Slick if you don't have it.
Yeah.
So I love my analyzer, my SSA, but it's a $4,000 investment. So you have to really love it for $4,000.
We don't love it that much just yet.
No, I get that. I got mine to start with. So back in the day when you didn't have it.
Well, it used to also be $1,800. And now
Yeah.
the only thing that they changed was it was a serial port, and now it's a USB port.
Yeah, which I had to buy the conversion for.
Yeah, very expensive cables.
Yes. Yeah, not very effective. Kelly asked about semester midterms. My midterm is the district's. I write the test for the entire district, so I'm not at liberty to share that. But if anybody else out there has a semester exam that they're willing to share, let Kelly know that. Kind of send that. The email has everybody's name on it, and it does in your cohort group. Those are all the questions that I had anybody ask me about up front. So, and it looks like people are, from what I can see, at the end of 1-3 or in 2. So. Okay.
All right.
Okay. Adam, you want to take us through where we left off last time?
Sounds like fun. So before we left for break, those of you that were here, we kind of like towards the end of the meeting, we finished up a trust calc, and then we got into our unit 2.2 here, lesson 2.2, which gets into our materials and manufacturing stuff. And it's kind of, you know, over the years, it's definitely adjusted and it's changed for the better. But it's still, I kind of do something a little bit separate, but we'll go through and kind of talk about what the activities are and the different PowerPoints that are involved in here and, you know, how we treat them. So we'll kind of back up just a little bit here. But it's also a unit if you know, like, oh no, I only have 3 weeks left, and you have to kind of rush through a unit. It's not a super heavy math-intensive unit as far as 2.2 goes. And if I remember correctly, I don't think there's any math in 2.2. It's just mostly knowledge and background information.
Yeah.
So before we kind of talked about the introduction to materials PowerPoint, which we kind of ran through, and it basically just gets us into how do we talk about different materials, how do we classify materials, and you know, then how do we use or choose different materials. One of the questions that comes up on the final, that's 1 or 2 questions that will actually kind of give you a scenario and have the students select the appropriate material for the purpose or whatever it might be. So it is important that they know the material categories and also, you know, how to say, like if a scenario is brought up where they need to build a shed in the middle of the woods and they have to hike 10 miles out to build the shed, you know, what materials are they going to use? Are they going to be using steel to make this shed that they have to hike out there? Probably not. So you have to think about the properties of the material and what it's going to do in different scenarios. So it's good to go over and have a good general discussion on it. One of the activities I didn't talk about last time was this one called product analysis. I don't know, Karen, do you do this one?
Nope. No, and I think that's probably the reverse engineering that Tricia was asking me about. And no, I don't.
Yeah, I don't currently do this. I have done it in the past because, again, I kind of switch it up and do something a little bit different. But it is a neat activity for the students to get involved in that can be a 1 to 2 day thing if you need to kind of cruise through it. But essentially, they're supposed to find some sort of product at home. And usually it's like a remote or a toy or some sort of plastic product that has multiple pieces. And they bring that in and they're going to take it apart. And they're going to, in their engineer's notebook, they're supposed to basically analyze its components, create a materials list, you know, create a parts list, put in there what, you know, describe the product, measure the components, do all sorts of different things to it. But really, they're focusing on just 2 of the parts of that product. So what I used to do is I would have the students pick 2 different pieces that were different materials. So they might not know that it's like if they both were plastic, I'd make them choose something else. So they had to know how to figure out that it's definitely a different material. So a metal and a plastic, or maybe an elastomer and a piece of wood, or whatever it ended up being from that product. And then what they would do is they would examine that. I'd have them go into Inventor, draw it up in Inventor. And what's nice about that is if it's a weird or awkward shaped component, in Inventor you can figure out the volume just by clicking a button, and it shows you what the volume of that component is. If you don't draw it up in Inventor, you can also do the whole displacement method for figuring out volume, where you just sink it in some water in a graduated cylinder. But just gives you different methods for doing it. So you go through, you pull those two components out, you sketch and design them, and then they run through a bunch of tests. And the whole idea is to try to figure out what that material actually is. And it's pretty easy to put it into a category, but how do you then take it out of that category and put it into its specific material? So they run a continuity test with your multimeters. You can just touch it to see if it has electrical conductivity properties. Does it have iron in it? Touch a magnet to it. Is it magnetic? What is their hardness? What we would just do is get a nail and we would scratch it. And we would say, did it scratch and chip off like glass would, or did it kind of like make a deep groove like a soft plastic? Looking at hardness, we would mass it, figure out the volume. And one of the ones that was really important for us was the density, because when we were looking at different plastics, once we figured out, the volume of this material, what its mass was, we can then figure out what its density was. And then you can actually go out onto the internet and you can find charts of plastics and what the density ranges are. And then you can figure out, okay, these two types of plastics are within this density range. Well, okay, let's see what they're used for. So they could go into research and figuring out exactly what those materials are used for, and then get a pretty good guesstimate of what it actually is.
Online. Yeah.
So they did go through a whole bunch of testing to try to figure it out, and then based off of their results, what they would get, we would kind of analyze it and see if they had a correct assumption or if there was some error in what they were doing. Any questions on that?
One of my friends, instead of having kids bring something, she just goes to garage sales and just, finds stuff that she can, her belief is for $5 she can fit a whole class with stuff to take apart. So that's always a thought, and often when she tells people what she's doing with it, they just give it to her. So so if your issue is that you don't want kids bringing something from home that maybe they shouldn't bring or whatever, that same friend started doing that because one of the kids brought their TV remote and took it apart, and so which was not, I have permission to do that. So she just gets stuff and brings it in. So that's always an option if that's a concern too.
Yeah, definitely something you always have to mention. This has to be something you don't care about. All right, so once we go through like looking at the materials and trying to analyze what the materials are actually made of and trying to fit them into categories, then we start to look at how do we actually manufacture these goods. And what I like to do every time is I open up this PowerPoint and then I point out in the lower left-hand corner here, which is where most students usually look right away. There's 46 slides to this PowerPoint. If you ran through this entire PowerPoint, you would just have lost every single student, even if you did it over a couple of days. It's just too much stuff and it's too dry of stuff. So you have to kind of break it down a little bit, use different methods to make it a little bit more interesting. But the gist, the main knowledge that they need to get out of this is the different types of manufacturing setups and the different ways that we process materials. For the most part, I don't think students are very aware of how to make stuff. They're inexperienced. They don't have a lot of time where they physically used a bandsaw or used a welder or used different things like that where they can actually physically make stuff. So they don't really have that background knowledge. And it is pretty important, especially if they are going to be engineers. They need to know how to make stuff. You can watch it on TV, but what's that background knowledge? So what ends up happening, you can click through this, I'm sure a lot of you already have. The first part again is the manufacturing setups, the difference between am I making one of these things? Am I making one of these things that's a cruise ship? Or am I making one of these things that's a little tiny widget? Or am I making a million of these widgets? How would I set up my manufacturing system in order to most cost effectively do this? And I worked at Pepperidge Farms growing up, in college and late in high school, and it was a great experience to see how they went from raw ingredients to manufactured cookie to packaged to out the door. And the plant was a quarter-mile long. So I quite often use that experience in talking about, well, we're making 200,000 cookies a shift. Are we going to be making them one at a time? No. So you kind of bring in that background experience. So what I do with this is I have a document that the students actually open up, and I break down the different basic setups for manufacturing systems here into a job shop, a flow shop, a link cell shop, a project shop, continuous process, and also lean manufacturing. And what I have the students do is just give me a basic definition of what that is, and then go out there and find a graphic or a YouTube video that goes over or explains, what that setup is. What would it look like? So they can get some sort of reference to, an example or something out there. So we get into that. We go over that. People show their different examples. And then the second part of it is how do we process the materials? And we'll find out that a lot of the students really combine these three into one category. So they have to really figure out what is the difference between casting and forming and machining. So they come up with some different examples of those. Not necessarily correct every time, but it gives them at least an example, and we can kind of tweak it later. So we break it into the different groups and categories here. One of the things I always bring up when we do the packaging stuff, when I was in Iowa a couple years ago, we went to a Oral-B manufacturing company, and they were manufacturing toothbrushes there, obviously. And one of the people that gave us the tour was a packaging engineer, and she talked about how extremely important her job was, because when they are packaging a toothbrush, they actually spend more money on the package than they do on the toothbrush inside of the package. So if she can cut what they use in the package down by 10%, she just saved millions of dollars. And so she was very boastful in saying they had the smallest package of any toothbrush manufacturing company and blah, blah, blah. She was very happy about it, which I can understand why. And note to self, when they manufacture your toothbrush, at no point do they ever clean your toothbrush. It's never sterilized. Because they don't physically touch it with their hands, they don't have to sterilize it. So if you're a germaphobe, maybe sterilize your toothbrush. So you go through that. We have them submit it. It gives them a brief background into it, and it's a hell of a lot more exciting than going through this whole PowerPoint and listening, which I'm sure would put them right to sleep right away.
So Adam, do you make that PowerPoint available to them if they want to use that PowerPoint as the resource, or do they go out on the internet?
Yeah, what I do is it's available to them. They have the whole curriculum, whatever they need, but I make sure that they have to go somewhere else to get the picture or the video, because I don't want everybody to fit within that cookie cutter PowerPoint that we already made. I want them to go out. There's millions of resources. They need to go out and find them. And it gives them a little more time to hit the hunt and peck.
How long do you give them to put that together?
Well, since I'm in a block, it's about an hour and a half, like 86 minutes. I'll introduce the activity, and then it'll be due the next day. And they're usually pretty good about getting through it. Some of them, if they dilly-daddle, they don't do it. But essentially one day, and then if they don't finish it, get it done for homework, and then be ready to go the next day.
Could you attach that to a reply
Sure.
to the email? Thanks.
Yeah.
That video, unfortunately for me, this unit comes up during enrollment, and this unit is the least exciting unit we teach. And so I try and do what Adam did, because it will kill children to watch both the materials and the manufacturing. And so one thing that I do is you do have some SME, study mechanical engineers, is that right? Send some videos. You can embed those in. And some of those are really cool. Like how you make plastic bags is totally cool. That's a very cool video to watch. And then cutting with water, water cutters, that's really cool. So my kids, there are some of them my kids like. One of the things I've also done, like what Adam did, is ask the kids to find movies that have the machinery in them. Like, it is a completely vacant foundry that the Terminator is walking through, though everything is still liquid and hot. So almost always Terminator movies come up with some of the manufacturing stuff. So they've seen some of it, they just haven't walked through it.
Yeah, and I think it does as a whole. Like most of the POE teachers, master teachers that I know of, this one, it's kind of a quick unit. Everybody kind of cruises right through it, but I think it is a really important a part of what we do. Just because it doesn't have math in it doesn't mean it's not, super important.
It is also tested. It is, there are material questions on the end of course, and there are manufacturing questions on the end of the course. So it would not benefit your kids for you to shortchange it.
All right. There is a manufacturing process activity that you could do after this, and essentially what you'll do with it is the product that the students took apart and analyze the different components. The two that they figured out, okay, this is definitely cobalt, and this one is definitely high density polyethylene. Okay, how do we make these things? And the students are supposed to do some research and figure out, okay, well, where do these things get made, and how are they made? So they can do some more research as far as usually YouTube videos are great, or just like Society of Manufacturing Engineer has tons of resources if you go to their website. But it can be a relatively quick activity if you need to progress through it. It can also just be done as a group discussion. They do get into recycling activity. We get into this whole presentation on talking about recycling, and obviously I think that it's not something that students are unaware of. What I like to do is I kind of like to play the devil's advocate here and talk about, okay, the benefits of recycling, but also bring up, well, here are some negatives of recycling, and it's not a flawless, process here. Just because we're melting down aluminum and reusing it doesn't mean that there's not also waste involved in that process. So they go through, and I think what's neat too is when you start to talk about download this, the different recycling facts. That's the rubric. As far as the like the plastic codes, what do those different codes mean? They get into the different reduce, reuse, recycle. This triangle, this circular process, and they kind of go through and break it down into some of our material categories here and how we can reuse or recycle. When I was at one of the summer trainings down in Rowan, New Jersey, or like Rowan, I actually got to tour a recycling facility, and that's a neat thing. If you have one in your area and you're allowed to take trips, it's a really cool thing for the students to see. It's not as automated as I would have thought. Just a lot of people kind of picking at things, but what was interesting, one of the biggest things I took away from it was the glass, because it was single stream recycling, meaning that you take everything and toss it into one bin and then you send it to them. Glass really can't be recycled in different colors. So if you have green and white and brown glass or green and clear glass, it gets smashed on the way there. what they do is they just smash it up a little bit more and they actually sell it to the dumps. And they use it as a fill that they put over top of, like as they fill the garbage at the dump, they'll put a layer over top of it in order to try to bring down the scent or the smell or whatever. So a lot of glass, you think you're recycling, it's just being thrown away anyway.
The recycling facility near us, I can't take students, but you can, as a family, go tour because of the liability of it. So it's on my list of, if I had a weekend field trip with my family, what would be a good thing to go see? And it's kind of cool. And ours uses big fans to start off to lift everything that's light, and then they hand sort from there. But so when you check it, you might see if it's something that you can take or not. But I just couldn't, as a teacher, the liability that you have to sign off to make sure nobody gets injured, I couldn't do.
Yeah, that makes sense. All right. This presentation is usually a relatively quick presentation, and I do it more as a discussion. The activity you can continue to take that product and go through the materials and look at, okay, you have the high density polyethylene. How do we recycle high density polyethylene? You know, it's a chemical process. What's involved in that process? And what is it? What are the products then used afterwards? You know, we're using some of these plastics for food grade initially, but once we recycle them, they're no longer safe for human consumption or even for animals. So you have to be careful of which materials you get for food for recycling. So these are a lot of different activities. What I try to do, because we've said before, it's not the most exciting section here, but it definitely is an important thing. So I'm always trying to make it a little bit more exciting and get the kids a little bit more interested in it. So a couple of years ago, what I started doing with the students is doing a chocolate manufacturing project. So the students, through the project, what I do is I divide the class into two teams. They create their own manufacturing companies, and they create a chocolate bar. So initially, they're broken into teams, and they have to come up with a design and figure out, okay, what's our theme for this chocolate bar going to be? And you know, once they figure out what the theme is, then they have to figure out, okay, who's going to do what. So they elect a president, and then they elect different positions as far as people that are really good in design. So if they loved using inventor in IED, maybe they're in that side of the game there where they're designing the chocolate bar. If they're creative, artistic people, they lean more towards the packaging or the marketing side of things. So I give them some constraints, not really too many constraints, but I make them all make the same size bar. Just for our purposes, it works out better that they're not trying, well, we're going to make 10-pound chocolate bars. That's not going to work out so well for me financially. So they all make approximately 2 by 4 inch bars that we then create trays and actually create the chocolate. Now we don't make the chocolate. I just take Hershey's chocolate bars and we melt them down. But from there on out, they make everything else. So I kind of have a process set up for them where they go through the design, and each step of the way, we're starting off with integrating those different sections we just went over. So we talk about materials, and we get into, okay, you're manufacturing a chocolate bar. What materials do you need? Of course, the first one always comes out as chocolate. All right, well, what are we going to pour the chocolate in to get it to be the shape we want it to be? You know, some of them will know that the real molds are made of aluminum. Some of them will think plastic, so we start to look at those materials. And then the students have to kind of break up and do some research on those materials and kind of follow the same process that we did already in the unit. Once we get into the design, that type of stuff, then we start to get into our manufacturing, and we take a look at, you know, how are you going to set up this manufacturing company? You know, is it going to be this type, or this type? What are you going to do? So then we start to talk about those different manufacturing setups, and then they integrate one of those setups in their process. So It's definitely an evolving process, and it can be a very quick thing, or it can be a something that takes. Typically, we spend about 2 weeks on this. In a block scheduling cycle, it's about 2 weeks to get through the whole thing. So this is an example of one of the groups that made one this past year. So they get through, and the designer will actually draw up what the bar is going to look like. We 3D print an example so they can get a a tangible idea of what it's going to look like. Was the text the right size? Is the shape the right size? Is everything right? If it is, great. If it's not, we have to change it up a little bit. So you can see they changed up their text size there. We reprint it. They do the whole packaging, so they get into Inventor, or we use another program called CorelDRAW, and they design it, and they have to physically, figure out what goes on a package and what's involved in that process. Then they'll produce the package to hold it. They'll produce the wrappers to hold them, and they kind of have like a process she put in here of how we went through. Whoops, did not want to do that. We have a plastic printer and a powder printer. The powder printer you can stack. I don't know how many of you have a powder printer out there. They're kind of old school. We've had it for like a decade, but you can stack that whole box full of print jobs, so it's just a little bit faster. The 3D plastic printer takes, if we were to do that, it would take a couple of days till we get through all of the ones that we needed printed. But essentially, we print the molds. Here's we're just kind of cooking them a little bit in order to vacuum form them. We have like just a little benchtop demo vacuum former, and we put the little examples in there, and you heat up plastic, and then you stick it and shrink it down on top of it, and then eventually what ends up happening, you kind of see in the background here, is you get the mold, the reverse, the negative of what we're looking for. And then they basically just use the chocolate to melt down to pour into there. Let it set up overnight or over the weekend, and then they go through, pop them out, wrap them in packages, and then they get a little crazy apparently. So that's just one idea, obviously, of what you can do to try to make, the manufacturing a little bit more interesting, rather than just, here's a PowerPoint, now do this activity type of thing. Any questions on this lesson? That pretty much takes us through lesson 2.2.
Hey, Adam, will you attach that outline as well?
Yeah.
The paper you just showed us?
Yeah.
Thank you.
It's by no means well done, but I'm constantly changing it to try to get it to get out of the students what I'm looking for, and it's constantly, okay, well, how do you word it better so that you're getting a better product in the end, so they know what you're looking for. But yeah, I'll email that out to everybody.
Yeah, it's at least a template because not everybody's probably got all those things that you have available, but it's at least a template for people to work with.
Yeah, and you can even, it doesn't have to be a vacuum former for the molds. We found you can do like 2-part mixes where you pour over top of stuff to get like a rubber mold. So you can kind of scale it down, do a little bit differently, but it's kids love to eat chocolate, so it ends up working out well for them. All right. All right, so that gets us through 2.2 then, and then takes us into the material testing section of things. It does start off with the material testing formula sheet. Now, if you have, like I do with my students, they all have the full formula sheets with everything. So they have it from day one. But this one kind of breaks it down to be a little bit more specific to what we're going to get into right now. So it's a good resource for them to be able to look back. Okay, I need to know what elongation is. All right, what's the symbol for that? How do I solve for that? They can find it all right here in an easy resource. Here. Then we get into the material testing. The one thing I didn't mention with the manufacturing activity, we do a little bit of material testing. We get into, chocolate's supposed to have a certain amount of, we'll call it elasticity. It should flex a little bit without cracking, but it should also crack once you flex it enough. And it should have if I push down on it, it should have a certain amount of resistance to it to be the right consistency of chocolate. So we do a little bit of force sensor pushing and pulling and stuff on it, and then we do the best type of testing ever for materials, which is eating it. So gets to be pretty nice. All right, so kind of run through this one because this one is not necessarily the most intuitive presentation, I guess, if it's your first time dealing with material testing. We get into static and dynamic testing. If you have the SSA machine, we create something what's called a dog bone, which is a sample piece of metal, and we create a weak spot in it so when we pull on it, we know where it's going to break. If you don't have the SSA, then we end up using the, I'm forgetting the name of it now, virtual tensile tester.
Yeah.
Which is a digital version of it, if you will. So we're going to be looking at tensile testing. Our machine, if you kind of change it up a little bit, can do a little bit of compression test if you have the SSA machine. Then we even talk a little bit about the hardness. If you're ever up in the Milwaukee School of Engineering area, this is actually the machines that they use. This is from that school. I think these are from like 1950. They're relatively old. They're definitely not digital devices, but it can produce tens of thousands of pulling pounds of force. And the sample piece that they break, when it breaks, it's a pretty loud snap. It's a pretty loud bang because some are breaking around 60 or 70,000 pounds of force. This is an example of the sample piece that they would do as an industry standard size. Ours is going to be a little bit smaller for the ones that we break if you're actually able to produce them. They end up being this 1/8 inch size, which I know a lot of people don't do this anymore. From the testing, from the results, whether you're using the virtual one or the actual one, you're going to get a chart that's going to give us information and looking at how much force was applied and how much did the piece stretch. And based off of the amount of force and stretch and whether it was proportional or not, it's going to let us see some information about that material. So the students get into some relatively new terms. This little guy is a little delta, a lowercase delta. And they know uppercase delta means change in. Our lowercase delta is basically looking at change in length or size, if you will. And they talk about with a uniform material, if it's, for example, brass, if one sample is 1/8 of an inch in diameter, the other sample is 3/8 of an inch in diameter, both of them are going to react proportionally. B is going to take more force to break, but proportionally more force. So if A takes 100 pounds, B is going to take the same amount as if it was only 1/8 of an inch, but since it's 3 times the size there, it's going to take proportionally that much more. They get into one of the first formulas we're going to take a look at here, which is looking at stress. And stress is basically looking at the amount of force that's applied per unit area here. So we're looking at if I'm pulling on that dog bone example, and I were to look at a certain point as I was pulling on it, how much load does it experience? How much force is being pulled on stretching that? And then we look at what our original area was for that weak section of the dog bone. So they give me an example here, 430 pounds is being applied, and we're looking at this area that we taper down in the center there, which we do intentionally when it's made so that we know it's going to break somewhere in here. We don't want it to break out here because it's harder for us to measure that, but because this is weaker and smaller, we know it's going to break in there somewhere. So we use that area. And doing the math, you end up getting about 35,000 psi. And you're going to find out most of the times when you get these answers, we're going to be rounding it to like 35,000 or 36,000 or something to that effect. When we get like the small, these last 3 digits here, they're not as important that you're writing 35,121. The other thing we look at here is the strain, and strain is basically looking at how much did that thing change compared to what it originally was. So we use the little delta here, the lowercase delta, and we divide that by our original length, or we say L sub O. The little epsilon here represents the strain. So for example, if we had this dog bone and we applied that force that we talked about before, and it stretched 0.0625 inches, we divide that by the original length. And notice the original length that we're looking at is just this weak section in here. It's not the entire piece, but it's just that section right there in the middle. And we end up getting our strain to be 0.0625. And Karen, maybe you can give me your input on this, but do you have any insight on what the unit should be here? Because sometimes it's left inch per inch.
Yeah, and in physics, we would leave it as inch per inch so that we knew what units we were working in. It is a unit-less result because those units cancel, but any physics that we do, we go ahead and leave inch per inch on it. Okay. So my kids will go ahead and will not put a unit on strain.
And how much of that is because they chose not to, and how much is they just didn't because that's what they do?
My kids can't cross it off, so they at least are mechanically programmed to cross it off. But yeah, when we teach physics, we leave inch per inch.
So yeah, either way, that's what I tell the students is either way it's right, and you can even go online and find arguments of people going back and forth. This is the way it has to be, and this is the way, but it's up to you really. I accept either. All right, so from our testing results here, what'll end up happening is we're going to get a graph that looks something similar to this. You know, depending on the material, if it stretches a lot and then breaks, or if it doesn't stretch very much and breaks very rapidly, you know, you're going to have a different slope here and a different amount of distance in this direction here. But each section, each little piece of this graph is important. So it's going to tell us some different things. So typically, unless you're working with something that's not really mounted well, or maybe a very specific type of material, but usually our initial response is going to be a linear response. So if I apply 10 pounds of force to that material, it's going to stretch a specific amount. So maybe I apply 10 pounds, it stretches a thousandth of an inch. If I apply another 10 pounds, it's going to stretch another thousandth of an inch. And all the math teachers out there love this because it gives them a great example to show students, hey, this is what's happening, and here's why we, do this in math. So it is proportional, and we also call this our elastic range. So if you were to stretch out that dog bone and then let go at any point in this range, it's going to return back to its original state. Pretty much every material has an elastic range. Some of them are larger, some of them are smaller. You think about something like glass, it's going to be a little bit smaller, but it has an ability to stretch, and then when you let go, return back to its original state. Our proportional limit is right here at the top, and that's going to be at that point where we now lose proportionality. So when I add that 10 pounds again, it stretches maybe 0.02 of an inch. So it's no longer the same proportions anymore. And what's really nice, and I'm not as well versed with the virtual tensile tester, but it's really nice on the SSA where you can look at the data points. So once you've tested this, you can actually go into the actual data points and you can see right where it went from adding 10 pounds, stretch to thousandths of an inch, adding 10 pounds, and all of a sudden it stretched 2 thousandths of an inch. So it lets you really see where that information is rather than just trying to guesstimate it off the graph. We're at here. Okay, so we get the proportional limit. We get into, when we find correct me with my terms here, but the slope of this line right here would be our modulus of the elasticity, right?
Right.
And
Rise of a strain. Yeah.
Correct, yeah. So we end up looking at our stress over our strain here. And essentially, the larger our modulus elasticity, which we should be able to take this back to when we did the beam deflection stuff. But the larger, the stiffer the object. The smaller the number, the easier it is to stretch. So you go through that, show that. You have your elastic limit. You have something which is known as our modulus of resilience, which is basically just the area underneath this graph, and underneath the elastic range here, which is your essentially 1/2 base time height, finding the area of a triangle. In order to do that, we'll use the stress and strain involved in there.
If any of you have any calculus students, that's what second half calculus is all about. Area under a curve or area under some kind of formula, so function. So I always pull this out in calculus and show them this as well. That this is one of the applications for why I care about the area under a curve.
Cool. And one of the things that I give as an example why this measurement's important, this modulus of resilience, I take it back to a car, and when you look at like a bumper or a crumple zone in a car, they design that car to be able to absorb a certain amount of energy so that by the time the energy gets to you, like let's say you run into another car at 60 miles an hour, the energy is able to dissipate, and then when it gets to you, it's not enough energy that it's going to end up really damaging you. So if they can measure this amount of resilience, how much energy does it take to stretch this material, they can start to look at, okay, well, I can dissipate a little bit here and I can dissipate a little bit here in order to make that crumple zone a little bit more effective. All right, so here's when we're looking at exceeding the elastic limit. And what ends up happening at the yield point is it's in some of these graphs, it's very difficult to find, very difficult to figure out where it's at. And even as an industry standard, they kind of take it a guess. They can follow the slope of the line, but they're not 100% sure exactly where it's at. And the yield point usually is just past that elastic limit. So what they do is they use a couple of different offset methods. One of the ones is a 0.2%. There are other percent offsets that they do. But essentially, they find that slope and they just adjust it over a little bit. And where that line crosses over is where they're going to call the offset, or the yield strength point.
You aren't going to see that point on any of your data. So you're not going to, if you do either the SSA, the real test, or you do that virtual test, that point's not going to show up. We're not going to take data frequently enough that we're going to see where we have that yield point, where all of a sudden we get a lot of stretch without much force. Mm-hmm. So it's not going to show up on there. So don't ask the kids to find it in the data by using the data, because it's not going to be, there's not going to be enough data to find it.
Yeah, what's also important to mention here is that, well, I think a lot of the students think, because now we're kind of moving into this plastic range here where I've stretched the object to this point, and when I let go, it doesn't go back to home. I think a lot of people think it just stays right exactly there, but it actually will spring back a little bit. It just won't return back to its original state. So we're now into this plastic deformation area here, and you can see that there's a large amount of deformation with not a lot of force changing here. And we're actually going to find out that where it reaches its maximum force, it's not necessarily the largest diameter. So this is right before, when we get it up to this point, before we get to our maximum tensile strength here, This is right before we start to get into our necking region, which gets in.
Go back to Adam, because I think that's really, this is, I do what Adam just did, where he just flips through, or I disable those slides. So as the cross-sectional area decreases, the load bearing increases. Why is that? And this, I think, is a super, I wish this wasn't here. And therefore, I flipped through like Adam just did. But I spent a lot of time talking to lots of people about what this is and what they mean by that. And the point is, if you are stretching something, and even if you think about like silly putty, and you grab silly putty and you start to stretch it, there'll be a point on the silly putty that gives a little bit, but it doesn't just give a little bit and then break. It gives a little bit, and then another part stretches, and then another part stretches. So you're able to stretch it a long way before it actually breaks. And the point is that piece that you stretch out doesn't stretch out and then immediately break. It stretches out, something else then stretches out, something else then stretches out. So the fact is, because that stops stretching, it's stronger than the other point that's now ready to stretch. And that happens until everything is as stretched as it can be, until the weakest of those points now can break. This is, in my opinion, more information than the kids need to know. So we get through this. I do not show them this question, and I don't mill through it. Just FYI. Adam, I don't know if you do, but
I kind of talk about it. It was a good. I think the way you explained it was good. I like that. But this is the example of strain hardening. As you stretch that out and everything starts to go this way, but it's stretching this way, they consider it to be strain hardening, and it gets tougher at that point.
Sorry, go ahead.
All right. So then we get into this necking region, which is really cool. When you actually get into, if you're breaking dog bones, you can watch videos of dog bones being broken. You can see where that's happening. And when it's starting to happen, you can see as this starts to taper in, and now you know it's going to break right at this point. And depending on how large the samples are, the ones that we broke when we're up in Milwaukee, I forget the exact diameter of them, but it's got to be at least 1/2 of an inch. But you can go up there, and there's 50, 60,000 pounds of force on it, and you can touch it. It's hot at that section. Not like hot enough to make you move away, but you can feel there's a temperature difference that's going on in there, before it will break.
We have a testing lab. Butler Manufacturing has one of its testing labs in the metro area, and they break for us inch diameter bolts. And so you can see the necking that occurs, and then what I like is the space between the threads gets stretched as well. But they break a bolt for us for each of my groups that goes through. And what I love is this broke at, I want to say like 400 and something thousand pounds. And so what I love is it's got a digital read on it, and so like the SSA 1000, like it breaks and it's like doink, and it startles the kids because it kind of jumps, but this sounded like a shotgun going off when it ripped. And my kids were watching, because I had them all write down on a piece of paper what they thought it would rip at, and then the kid that's the closest gets the bolt. And so the great thing about it is the force is going up, going up, going up, going up, and the force started to go down. And my kids were like, oh, it's going to break in a minute, it's going to break in a minute. So I was so pumped that they knew that the maximum force is not where it breaks. It's on the way back down before it has that rupture point. But Honeywell Engineering, their testing center in their building also has a big tensile tester, and so look at, if you're close to a university or you're close to any steel manufacturer or testing center, you might see what they've got. This field trip, my kids have to sit through like a 20-minute lecture on pre-made prefab buildings that is mind-numbing if you are a teenage boy or girl. But going and watching that bolt get ripped, it's like people walk into my class the first day and they're like, are we going to go see that bolt get ripped? I mean, that's It's like something that's infamous. So that's like a go-to thing if you can find anything around you that does that.
Yeah, it sounds like an awesome testing. So some of this presentation then just finishes up with looking at, okay, once you do break that dog bone sample, not only are we looking at the chart, but we need to look at the actual sample and see how it broke, you know, and we can kind of figure out different things. And they give you some common sample pieces here and what they actually will look like as they crack. And it is important you go through a little bit of discussion on the difference between if something's brittle versus something's ductile. Most of the students know malleable. Like, if it's malleable, what's that mean? Okay, you can shape it. But ductile is something that they're not as familiar with, even though it's very similar. So they get to find out that if I have this really long deformation here, it's going to be more of a ductile material than if I have just a small deformation here. So I'm going to apply a lot of force, and then all of a sudden it's going to snap pretty quickly. And that's going to become more of a brittle material. So just looking at the chart, they need to start picking up different things before they even go to analyze. They should be able to see these different things. And then they get into the modulus toughness, basically looking at the total amount of energy here that's taking to break this piece, whatever it might be. And the one example that I use with this is a shear pin. So if you, an example that I have back in my childhood was we were drilling out a hole for a post, and we were using a big auger bit in the back of a tractor, and it hit a rock or something, and the auger bit just stopped. But the motor was still spinning the PTO in the back, and what ended up happening was the shear pin that was connecting the two together snapped. But it didn't snap the big auger bit, which probably cost $1,000, and the shear pin cost $20. But how did they figure out that shear pin was going to break before the auger bit was going to break, before the axle that was coming off of the tractor was going to break? And some of it was testing, but a lot of it has to do with this modulus of toughness right here. So they go back to the machines that they had, and they talk about compressions being done under here where they're actually able to squish it. This is actually a hydraulic machine, which is kind of cool. You can increase or decrease the speed of flow here, and they can just put tons and tons of force. There are different hardness tests as well, and it's usually for a hardened plastic or metal or glass or something to that effect. These don't work too well on, like, if you use, like, what's the hardness of silly putty? Doesn't quite work out the same. But what they do with them is there's a machine that, I forget if they have it on here. They don't have it on here. They basically just have a tip on it, and they put the sample piece that's usually flat, and there's either a steel ball or maybe a diamond tip or something to that effect, and they push down into the material. And the amount of force it takes to make a certain size dimple, they end up looking at a chart, and it gives you what the hardness scale is, or the hardness measurement is for it. We don't get into any of this. We just basically talk about the tensile testing stuff. But it's important that the students know that there's some different types of testing out there. And that pretty much wraps up our material testing stuff.
So 2 weeks from now is January 19th, which I think, though seems like no holiday that's going to keep us from coming back together again. But Adam's going to send out a couple of things he talked about, and then if you guys have any questions, just shoot us an email, or let us know what you need between here and there.